So let's see. We talked about exponents, exponential functions. You don't need to write this down. This is me sort of I like to talk and draw while I'm talking here. We've talked about how to convert that to logarithm. So that would be like log base a of x equals y, since f of x is y. We talked about graphing the exponential. So a to the x normally would tend to be something kind of like this, unless a happened to be negative, in which case it would look like.
Wait, wouldn't it be log a y equals x?
Yes. Surely. You learned it, but I didn't. Yep. Log a y equals x. We talked about if there was maybe a b value right there, and that b value was negative, then you had exponential decay. So we talked about that graph. Are we rolling? Okay, awesome. Or maybe a was negative and b was negative, in which case you had exponential decay going from here. Something that we haven't talked about are the graphs of logarithms. What does that look like? We've already taken the exponential and we've reflected it and reflected it this way and stuff like that. So what's left for a logarithm graph to be? I don't know. Let's find out. So today we're talking about logarithm graphs. We're also going to teach you something that I have always sort of neglected. It's sort of like the lost lesson when it comes to logarithms, and that is log plots, okay, and how that relates. So I'll teach you that to you this year, and then you will be set for life. So here we go. We're going to say y is equal to log base 10 of x. And like all good graphing, we're not going to use the calculator yet with the graphing mode. We're going to build it with a table so you can actually see what's going on yourself. So there's x, there's y. But you probably don't have different log base 10s just sort of in your mind. But what you probably do have is, let's go ahead and rearrange that to an exponential equation. So let's turn y equals log base 10 of x, that logarithmic equation, into an exponential. Emily?
10 y equals x.
Okay. 10 to the y equals x. So if we wanted to play the normal game and just throw up x values there, then we could, but then you've got to kind of go in your mind to figure out what would be a good x value that would match a y value, blah, blah. That's kind of ridiculous. But in this case, we're going to have some like y values, all right? And we're going to come up with some y values and then throw those over and figure out what the x value is. So for instance, good old -3, -2, -1, 0, 1, 2, 3. You might be able to do some of these in your head. So for instance, 10 to the 0, 1. 10 to the 1, 10. 10 to the 2, 100. 10 to the 3, okay. 10 to the -1, 0.1. 10 to the -2, 10 to the -3, 0.001. So, if we look here, so draw some x values. All right, an x value of 0.001, so that's like right here, is a y value of -3. So right about there. An x value of 0.01, so just barely this way, is -2. An x value of 0.1 is -1. So right there. An x value of 1 is 0. 2, 3, 4, 5, 6, 7, 8, 9. 10. So x value of 10 gives us a y value of 1. An x value of 100, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 is going to give us a value of 2. Wow. All right. And next value of 1,000, so about to the sidewalk out there, we're going to be at 3. Wow, this thing is really growing very slowly. In fact, we find out that it's asymptotic there at the y-axis. Slowly growing, slowly growing. Oops. All right. Now, what does that look like? How would y'all describe that in terms of things that you already know?
Exponential.
Okay, it does kind of look like an exponential.
But sideways.
Yeah, sideways. Technically, it's actually reflected across the y-axis, or the x equals y. It's reflected across this line right here. You can say it's like an exponential growth or exponential decay, if you want, depending on which way you want to look at it. But we do see that it's growing, but sideways sort of here. And then it does approach this this y-axis. So since we're talking about this, might as well talk about the domain and range. The domain, what are acceptable x values? From the graph, it looks like it's got to be greater than 0. From up here, we can see that it's whatever you can put inside a logarithm. Going over here, we've got anything to a power. If you have power to a power, and if these are all positive, even if these are negative, all right. If y is positive, you're going to have 10 to 100, 10 to 1, 2, 3, so 10, 100, 1,000, 10,000, 1 million. So those are all going to be positive. Even if y is negative, okay? What happens if y is negative? Like with the negative,
It just becomes a fraction.
it becomes a fraction. It becomes 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000, 1 over, okay? And so it's still going to be a positive or positive. So no matter what, x has to be positive. So x is going to be greater than 0. You're never going to be able to get 0 or a negative number if you always just have positive in the numerator, positive in the denominator. And the range, yeah, all reals. It actually goes down really, really quickly, but it'll continue to go down to negative infinity for the y value. And it'll grow eventually, and it'll hit 4, and it'll hit 5, it'll hit 6, but it's not going to hit 6 until you're at 1,000,000. Okay? It's not going to hit 9 vertically until you're at 1,000,000,000. Okay? It's just going to keep going. But eventually it'll get up really high. So the range, all reals. So we can put it in your little notation here. From negative infinity to positive infinity. This, as we would call it, this is very slow to grow. All right? Because you can see going from 10 to 100, it only goes up by a factor of 1. Okay? Not by a factor of 1, but like by 1 unit. It goes from 1 to 2. In fact, from 1 to 10, it only goes up. What's interesting, you might think, okay, going from 1 to 10, it's going to go up by 1. Going from 10 to 20, it'd go up by another 1. And the answer is no, that's not how it is. It goes from 10 to 100. I said, what about by 200? Then it's going to go up another 1? No. From 100, it's going to take all the way to 1,000 to get up. So it takes longer and longer each time to get higher. Does that make sense? Mm-hmm. So this thing is growing ridiculously slowly. And it turns out that we see this a lot out in nature and all sorts of different things, even with music, which we'll talk about here in a second. But let's wrap up our discussion on these graphs here. So transformations. It's not enough to just graph it. You've got to shift it, move it around, do all that kind of stuff. So, for instance, if you have y1 is equal to log base a of x, and y2 is log base a of x, I'll put the parentheses there, and then you do plus k, go ahead and make a prediction. What is that going to do to the graph? What is that plus k going to do to the graph?
Shift it up or down.
Shift it up, yeah. Minus k,
Down.
we'll shift it down because that's what we're doing with those y values. We're already evaluating this. We're getting the same values that we had over there, but then we're just pushing them up or pushing them down. If we have y3 equal to log base a of x plus h, it's what we've seen over and over. We saw it with sines, we saw it with exponentials. The plus makes it go to the left, and the minus makes it go to the right, because it's sort of like catching up. All right, and so your domain and range might shift accordingly. Let's go ahead and on your calculator, go ahead and graph for y1 log of x, and for y2 log of x plus 5. And let's talk about the domain and range on each one of those. We already said it's going to be shifted up. So. Show me those graphs as I'm walking around. First one. You didn't put it in the parentheses. That's what I want to see. Looks good. Yes. Good job, ladies. Check values in window. Go to window and then zoom standard. Or zoom to the zoom standard. Yep. Oh, and no one's asking me if you need to be in radian or degree mode. I'm so proud of y'all. That's like a first semester type question. Yes, yes. Carly, did that fix it? Okay. Alright, so purple graph here, it's kind of bent, but that's alright. Talk to me about the domain of this second graph here, folks. What are the possible x values? Okay. Still, the domain, the x have to be greater than 0. Okay? Oh, we'll put that in our notation form. So 0 up to infinity. We cannot equal 0, so that's why I put the parentheses. Infinity always has parentheses. What about the range? What y values? Say again? All reals? Yep. But I don't think we have an all reals button, so we'll just say from negative infinity to positive. And one more graph. This is the Kevin graph. Log of x plus 5 in parentheses. Which way is that going to shift it, Kevin? To the left. So that one. 2, 3, 4, 5. There's an asymptote right here. Asymptote is 5 left from the previous asymptote. Somebody talk to me about the domain. Yeah, all x is greater than negative 5. Which, if we write that in set notation, set builder notation, negative 5 to infinity. Somebody else talk to me about the range there of that green graph. What y values? Yeah, it's still everything there. Okay, we can. All right, great. Everybody likes logarithm graphs. They're real easy going. Okay, they don't make any drastic changes. All right, it's pretty much business as usual. They're very steady, calm. We like that. Now, that's enough to get you through a little bit of the homework. Let me give you a little bit more here. I'm going to draw a new graph. I want you to draw this graph. And this one's going to be kind of weird. So, just a regular graph. But what I'm going to do on this x-axis, so that the y-axis, normal, 1, 2, 3, 4, 5, 6. On my x-axis, the distance between each one of these little tick marks is going to be the same. And I'm going to put 1 right here. But on this second tick mark, I'm not going to put 2. I'm going to put 10. So basically what I've done is I'm changing the scale of the graph between every increment. So from here to here, that's 0 to 1, so that'd be 0.5. But from here to here, I've changed the scale. This is now 10 units, the distance between my fingers, and that's 5. So it's like there's 10 of these within here. And then I'm going to do the same thing over here. This one's 100. I'm changing the scale each time. This one will be 1,000, 10,000, 100,000.
Would it be linear then?
And 1,000,000, 10,000,000. Now what were we saying?
Now, wouldn't it be linear, like if you plotted it?
Possibly. Ooh, I like the intuition there. So before we get to doing any plotting, I'm going to rewrite all of those numbers as powers of 10. So for instance, this one is really 10 to the first. This one over here is 10 to the 0. Maybe I'll write it in red. So 10 to the 0, 10 to the first, 10 squared, 10 cubed, 10 to the fourth, 10 to the fifth, 10 to the sixth, 10 to the seventh. And then, oddly enough, I'm going to change this again. And I'm just going to write the exponent. So this is 0, 1, 2, 3, 4, 5, 6, and 7. But for the units, when I'm labeling this, I will say that this x-axis is the log base 10 of x. Okay? Because remember what logarithms mean. Show me the exponent. So I'm telling you that this x-axis is the logarithm values, or they're the exponent values. Now, I don't have it since I have it on a previous slide. If we were to start plotting those points, okay, when y was 1, what was the x value?
No, wait, sorry.
When y was 1? 10. So when y is 1, we're at 10. When y was 2, we had 100. When y was 3, we were at 1,000. When y was 4, 10,000. When y was 5, 100,000. Y was 6, we're at 1,000,000. That's off the grid here. But ooh, intuition paid off there, absolutely. When we graph a logarithmic function on what's called semi-log graph paper, okay, or a logarithmic x-axis, what really took a long time to grow, okay, here looks linear here. In fact, it was so should be a line. This is called semi-log graph, or sometimes called a semi-log plot. Semi meaning half. This half, the x-axis half, is a logarithm scale. So I'm going to try something. I don't know if it's going to work.
No one knows.
All right. So here's my x. Here's the y. And what was that? Y equals log of that cell. Well, that's not very helpful. So, 0. Oh, it can't equal 0. 1. Okay. I'm gonna nope. That's the URL. Let's copy this. Yeah, I told you I'm terrible at this. 10. 100. 1,000. This one's going to equal that one times 10. And I'll copy that here. Okay, great.
So don't you just love Excel?
What's that?
So don't you just love Excel?
Well, yeah, this is sheets, but it's kind of nice. All right, so let's see what I can do here. I'm going to plot this. Insert chart, maybe? Yes, insert a chart. Huh, a line chart. No, thank you. I only like XY plots. So there's a scatter plot. That's terrible. Look at this. It's like, look at my X and Y axis there. This is a linear, I go from 0 and then 250 million or whatever, right? And all my points are all squished right there, okay? And then I get 1 point over here and 1 point right up here. Do you see how terrible that is? Right? Because like, all those values, can we move this guy? Maybe not. Whatever. There it is. See, you know, for an X values gets really huge, and these are just going up little bit by little bit. So this is, do y'all see how this is like really not helpful at all? Okay, because logarithms, they grow so slowly. This one they said 1 to what is it, 250 million or something like that, and all those points right there. Okay, so we're gonna fix this. Edit that chart. We'll customize it here. Horizontal axis, please. I don't need to label any fonts. Oh, what's this? Log scale. That looks like the exact button I need. Ta-da! There it is. So you notice we've got 10, what was that, 1,000 or something like that?
10,000.
10,000? Like 10 million maybe? 10 billion? Look at that. It's really nice. And if you didn't know this, but if you were looking at a semi-log plot, then you might say, oh, it's linear. Wrong. This thing's not linear at all. This thing doesn't grow anywhere near as fast as linear. This thing grows logarithmic, which is super slow. For those of you that plan on taking computer science too, we'll talk about logarithmic graphs next year with computer science, because you end up running programs with millions or billions of connections, and you need it to grow logarithmically rather than linearly. Otherwise, your programs will never get solved. If you're curious, what sort of programs could that be? Oh, I don't know, maybe like Google Maps that have lots and lots of data points that you need to process, or maybe Google itself with all the different searches. Or, believe it or not, pretty much any company with lots of products and lots of sales and stuff like that, you need to process stuff a lot. You want it to run logarithmically rather than linearly. Let me see if I can show you why that is. Let's just say that we have a very, we'll call this, I'm going off script here, call it Z. And this is just going to equal, it's going to be a linear graph. It's going to equal that. It's just going to be linear. It's going to equal that one. All right. So I wonder what a linear graph looks like here. Data. Can we add another series? Let's select the data range.
You need to write in the data range.
I got to write in the data. Oh,
Yeah.
that's ridiculous.
Which is really
D.
D2, D14.
D2.
What is this nonsense?
What happened there?
Now we have a linear y-axis.
Still have linear y-axis, but look at that y-axis now.
It's ridiculous.
It's huge. Why is that y-axis going huge? Because look at these y values. I don't even need to do a graph. Look at how fast the linear grows versus the logarithmic. Okay? The logarithmic, by the time we get down here to 10 trillion, the logarithmic is sitting at 12. The linear is sitting at 10 trillion. You see what I mean? Would you rather have something that was maybe a problem that you were trying to solve grow logarithmically or linearly? You probably would rather grow logarithmically because it'll grow slower. Okay? That's not what I wanted to do. I don't want to do that. So one thing that you can do with this, it's possible to also get logarithmic stuff on your y-axis. So we'll do that as one of the last things we'll do. So we'll customize that. Vertical axis. There's that button there. Here we go, log scale. That's great. Default, that's the scale factor, but log scale is perfect. So this is really great. This is going to show us how fast those things are growing relative to each other. Okay? And you can see the blue is the y, which that first one, that's the logarithmic. So this is the logarithmic growth. It's growing, but really slowly. But then look at the linear. That's taken off. Okay? So if maybe this is the number of data points, and this is the number of hours that it's going to take, or even the number of minutes for your program to run, then you want something to be running logarithmically rather than linearly. Okay? And this type of plot is called a log-log plot. Okay? The other one was called a semi-log, so it was just half. And it used to be, before they had that button on Google Sheets and on Excel, oh, there's Google Arts and let's look up semi-log people. If you were in engineering, or if you were in pre-cal, you would have to buy graph paper, ladies, not just regular graph paper, but you'd also have to you have to buy semi-log graph paper or log-log graph paper. And it would look something weird like this, where you would go from like 0 to 1, you know, and then this would be like 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. They'd get shrinking smaller and smaller, and this would be 1, and this would be 10, and so this would be 2, 3, 4, 5, 6, 7, 8, 9, and this would be 100, and so you'd have 10, 20, 30, 40, 50, 60, 70, 80, 90. They get closer and closer, and so you'd have to buy paper like that, and you have to graph it. And then you can also get log paper, which has it going on. Well, this is the semi-log paper vertical, so because I typed in semi-log. Anyway, and then you'd have to plot it and do all sorts of other stuff. But why bother with any of that? Now we've got the calculator. The computer can do the log plot just like that. I haven't messed with it on Grapher. I haven't messed with it on your calculators. But this is something specifically if you're going to go into a math or science. You know about semi-log plots, you know about log plots. If you don't go into those, then you never know. Sometimes some of that information can help you. All right, and there's more stuff that we can say about that. In my engineering class, we talk about power functions turn into linear on a log-log plot. But I'll leave that information for next time. All right, you've got a little over 10 minutes if you want to start working on those programs. Not programs.